All right, so let's go ahead and try this one. This would be a good review as well. We've got a 5,000 kilogram roller coaster car starting from rest at the top of a 75-meter hill, and we want to find the speed at the bottom of the hill if the average frictional force is 200 newtons and the length of that track that it goes through with the friction is 110 meters long. So this is getting, to something that's very, very critical where we're looking at a change in energy. We have friction involved. And so yeah, go ahead and pause the clip and solve this one. And when you're ready to check, you can hit play to continue. All right, so our non-conservative work, we have our friction, we have our displacement, and we have our angle. And the big thing with this one is it's going down, but the friction is back. It's 180 degrees, and so we must have cosine of 180, and that's a really critical part with non-conservative work. The friction is always opposite the direction of the motion. And we're looking for the final speed. The initial speed is 0, the final height is 0, the initial height is 75, and so it should be 38.23 meters per second at the bottom. All right, so for power is the rate at which work is done, and we look at work in joules in time in seconds. And when we have the same amount of work, but the time is different. For instance, if we run up the stairs versus walking up the stairs, same amount of work, but if time is small, the power is going to be large. Also, power is force times velocity, and you should be able to get that from the power equation. Power equals work over time, which is force times displacement times cosine theta over time. So displacement over time is velocity. So force times velocity is equal to power as well. And dealing with a constant velocity here would be that. All right, so here we have a world record here as the person climbs the stairs 1,600 steps of the Empire State Building in 10 minutes, 59 seconds. The height gain for each step is 0.2 meters. What's the man's mass, or what's the average power output? So you got to remember with this, right? And this is a classic example where you have a person that's going, and as they go, their force applied is up, but their displacement is kind of up and over. So you only count what's vertical, and that's critical for this one here. So yeah, go ahead and pause the clip and do this one, and when you're ready to check, you can hit play to continue. All right, so again, only doing work in the vertical. And each step is 0.2, and the total amount of steps is 1,600, so the total vertical change is going to be 320 meters. And we have the force, which is equal and opposite of the force of gravity, so 70 times 9.8, and so 219,520 joules in 659 seconds, so it'll give us 333 watts of power. All right, so with circular motion, some important things to remember. The force is the centripetal force. Remember, centripetal force is inward. The acceleration is also inward. Velocity is tangent to the path. And F equals ma, right? So v squared over r is the angular acceleration, and or centripetal acceleration. And yeah, we can use that. And so we'll review here a little bit. So in this one here, we want to make a catch. We're turning to catch a pass. The radius of curvature here is what we want to find out. What's the smallest radius of curvature possible if the coefficient of friction is 0.4 and our speed is 5.4 meters per second. I also pointed out in class how important it is. Remember, in this case here, it's the force of friction that's causing centripetal force, and we always have to the center of the circle positive. So that's critical here. So yeah, go ahead and calculate the minimum radius that's possible, and when you're ready to check, you can hit play to continue. All right, so we've got our coefficient times the normal force, and for friction, positive towards the middle. And then normal force is equal and opposite of the force of gravity. And so therefore mass can cancel from both sides. And our radius, the minimum radius is 7.44 for friction. So if we did a tighter radius, If we were turning here and it was a tighter radius, we would slip. We would exceed the coefficient of static friction, and we would start to, we'd start to slide. Now, with twirling a bucket, this is another one where it's really critical to get this right. This, we've got the bucket up here, and here's the center of rotation in the middle. Now, again, remember, well, let's look at the context. You have a bucket of water that's on the end of a 1.3 meter long string. What is the minimum velocity you will need at the top of the loop to keep the water, just to keep the water in the bucket, and so that it'll feel weightless? And so, go ahead and draw the free body diagram. Remember, down is, or to the middle is positive. And so this one here is where it's weightless. It feels, there's really just that that feeling at with the water as it goes around the top. So go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so for this one, we should get the only force to the middle is the force of gravity. And now, if we were swinging it faster, there would also be a force of tension that we would add to force of gravity. But if it's weightless at the top, there's just the force of gravity, mg, and we're looking for the speed. And the speed comes out to be 3.57 meters per second as it spins around. Now, at the bottom, let's say that we're swinging this bucket still at the bottom, and we're swinging with the same speed. Again, to the center is positive, outside is negative. Go ahead and draw the free body diagram, set up your sum of the forces, and calculate what the force of tension would be as it spins around. So yeah, go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so force of tension in the middle, force of gravity down. So we have the positive force of tension plus the negative force of gravity, and we should get 196.04 newtons for that one there. All right, so let's say we're going over this overpass, and it's not a snowy day like this, ice day, and we're going over this intersection. We're going to feel kind of weightless, right? So let's go ahead and try this one here. We've got a car that's going over a hill or a intersection. The radius here is 17 meters, and we've got our car, which we're going to want to draw. So we want to find out what is the speed at which, or the velocity at which we're half our normal weight. So go ahead and draw the free body diagram, and then set up your sum of the forces, and figure out, how fast will we be if it's half our weight. And so, pause the clip, and when you're ready to check, you can hit play to continue. All right, so half of our weight would be half of the force of gravity, which would be half of, that value there, 16,660. And so therefore, our normal force would be 8,300, and our force of gravity would be the full force of gravity, and we could figure out the speed, and we would be going 9.13 meters per second over this road if that's what we felt.